So I'm going to talk about something that we've been working on for the last year and a half. Just to present myself, so I'm in the research center at Jülich. This is in Germany. I have a group of about, let's say 10, 15 people. We're working on different things. This is the one that I think is closest to the topic of the LT, which is why I'll be presenting it here. And so it's called neuromorphic principles for self-attention. We're really interested basically in understanding the overlap or the world in between transformer self-attention and neuromorphic hardware, and maybe even pushing this to the neuroscience. Okay, so so why are we interested in transformers and self-attention for neuromorphic hardware? Well, one of the big bottlenecks of a generator of transformers is actually in the self-attention block. So in the self-attention
Emre,
yes.
Please just look at your laptop screen and point with your mouse. We can see your mouse.
Okay, I'm not pointing to anything right now.
Okay.
So coming to the bottlenecks of generative AI, so what we have here is that if you look at the number of bytes that you pull from memory versus number of operations you can do for it, this is called the ratio is called arithmetic intensity. The arithmetic intensity basically tells you how much you can use. We was talking yesterday about these roofline plots. So they're essentially defined by these arithmetic intensities. And so GPT-2, which is this generative AI model, basically can only do 2 operations per byte loaded. And the reason for this is because it's inherently a sequential operation. You have to pull the KB caches from the memory, do those operations, and put them back. Okay, so this generates a lot of traffic. And so there's, of course, things that we can do if we build all of these things, if we build the memory closer to the processors, and that's one thing that neuromorphic hardware can do. It's interesting to note that actually most of the transformer models used today, even on GPUs, are highly, so the algorithms are highly co-designed, designed for the GPU. In fact, if you look at flash attention, flash linear attention, and so on, what they essentially do is taking the memory, so the KB caches. For those who don't know, actually, I will explain what KB caches are, but basically they're the token memories that are loaded into the self-attention. In flash attention, this is basically chunked and brought to the SRAM of the GPU processor and processed there as much as possible. So this increases the arithmetic intensity and therefore the speed at which you can run the self-attention operation. There are several different ways of accelerating this, but all of us, when we train transformers or Mamba and so on, we always use these highly engineered self-attention algorithms. So I'm interested in looking, so what can we do from a neuromorphic engineering, neuromorphic hardware perspective to improve this? And you'll see there's a lot of cool things that we can do. So this is, I'm sorry for those who already know about transformers, but I think this is a nice view of understanding how transformers operate, what they actually are. In fact, they're much more, in the way that we use them, they're much more like associative memories and actually attention as we would understand from a neuroscience perspective. So this here is the basic operation of the self-attention block. So basically you have some output, which is a softmax of queries, keys, and values. What does this mean? So let's take an example that, let's say you're trying to write a book, okay? And you're not very creative, so you're basically just looking the contents of the book on the Wikipedia page, okay? So each page that you're looking on the Wikipedia is basically your input token X. Let's say we want to write a book about thermodynamics. So the first thing I look about, say, is going to be free energy. So what you do here is that you take the information from this Wikipedia page and you write it in one book, in one page of your book. And so this has the contents summary of what free energy is. And while you write, you're also keeping an index table. So basically at the end of the book, you have your index table. And so this is at page 1, we know that we're going to find the concept of free energy. And then we just continue like this. We just read different web pages, one after another. And every time we do this, we add a page to our book and an index here. We'll just continue doing this until the end of our book, where we have, say, entropy, whatever. And we have, in the end, P pages, one for each page that we, web page that we looked up, and T keys. So now that we have this, so these two things, by the way, I mentioned key KV cache. So this is the key cache, this is the value cache, and together they call the key value cache. We can now use these caches in order to query something, to ask a question. So we might come in and ask, for example, what is free energy? So the way that you do this in a transformer is basically to multiply your query vector, which is some representation of your text free energy, times the key, the matrix of key, which is basically this page here, if you like. And this gives you a vector that has a high score on page 1, of course, because if you're coming with the question, what is free energy, we should get actually a high score on free energy of the first page. And so this should return actually the contents of that page. Okay. We can come in with a question that is a little bit less obvious, which is like, what is free energy principle in information theory? This should be a mix of what's on the first page and the last page. Okay, this is essentially what self-attention is doing. There's also basically the soft max here that just sharpens a little bit this vector here, but that's the idea. Technically, this is a little bit more like cross-attention, because usually in self-attention, this Q is also comes from the web pages, from the original vectors X. Here, the query came from another source, but that's fine. The principle is the same. Okay, so that's what self-attention is. It's essentially a heteroassociative memory.
Henry,
Yes.
and what typically is the most common operator to really find the closest match to the
Yeah, so this is basically the stop part. This stop part.
Dot
Stop part of
That's
attention.
it.
That's what
Okay.
transformers and many people are in the attention heavy.
That's okay.
Yeah. Okay. So now I'm going to. So how is this relevant to us? I told you about neuromorphic hardware, how we can do this in a neuromorphic perspective. Well, let's first look at one of the problems of the self-attention. So this is that, and of course, you know that the memory is going to grow with the sequence length. In fact, I was adding page after page for every token that I was looking up. And so this is not ideal if you want to build hardware. This demands a lot of memory. And so there are ways of overcoming this, especially going towards RNNs and so-called linear attention models. And the way that these work is for the linear attention models, just firstly get rid of this softmax operation. If you do this, basically you can put the parentheses around the K and the V, and basically you get this query times the key cache times the value cache. Okay. Now this is a really, I think, simple way of seeing and understanding what self-attention also is. If you can see this KV product as a weight matrix, in fact, if you multiply, you do get a weight matrix that's a fixed size because you actually multiply them along the token dimension. This is like a weight matrix that's changing as you're feeding in data. Okay. And that weight matrix is being used just like in an MLP, where you basically multiply that query vector with that weight vector. So essentially, self-attention is also like an MLP whose weight is changing during the input sequence. In particular, in this case, in the linear attention case, that weight matrix takes the shape of these outer products of each K and V token. Right? And outer products of two vectors is basically, you can see this as Hebbian learning. Okay. And this is what was nicely presented in a couple of years ago in one of Schmidt-Huber's paper, was saying that, well, actually linear attention is doing a Hebbian update. And this, of course, just should ring a bell to all of you, saying that, well, if W does act something like an MLP and that's undergoing Hebbian updates as we're presenting input tokens, maybe what is happening here is that this is actually a form of online learning.
If it's really just an outer product, then it seems very stupid to turn it into a matrix and then use that matrix.
Well, but you have plenty of them, right? It's not, but you're gonna basically add them one after another.
Yeah.
Right. I mean, it's just what you do with Hopfield networks as well, right? This is how you train. You don't really train it. You just basically take a W. That's exactly that.
The outer product. Yeah. But I'm saying to use all that memory when you basically all can keep it compressed as the vectors.
That's true. In fact, mostly in self-attention, you never keep the matrices. You actually just keep the keys and the values. But it's going to be different as you start making this a little bit more complex, right? So if you look at the Mambas, the gated attention and so on, essentially what they do is that they add gates, data-dependent gates to this W term here, as we have here, and to these KB outer products here. Okay, so different ways of actually choosing these A's and B's can give you different models. I have a table there later that can explain what some of those models can be. And so a couple of, let's say like a year ago, there's been this interesting thing saying that, well, if this is doing something like learning, right, then what if it uses gradient descent, right? And you might have heard of test time training, or yes, I guess it's called test time. So test time training is one model that essentially builds this weight update using the gradient descent on some loss that is local to that layer, right? So this, you see, this takes pretty much the same shape as this. And depending on the loss function that we'll be choosing here, we will be getting different updates. So what are those loss functions? There's a very nice paper called Gated Delta Networks, published, I think, last year, which basically lists the different types of models that are used in the literature and the online updates that they generate. So S here is like the W that I had. So if you take linear attention, it's basically as if you had some regularization loss plus some basically dot product here, and this gives you this outer product update. But if you look at the different, so you can see this for different Mamba models like Mamba and Delta Nets. Basically, these all have these different types of online updates, and these models perform really well. So if you, I know this is a little bit small, but basically all these models that are based on these learning objectives tend to work really well on the classical cognitive sense reasoning test. In the LT group, I've been labeled as the HGRN hater. And so this is why I've actually highlighted it here. Is why do I don't like it so much? Just because it really lags behind all of the other models that are actually equally simple and that are based on these learning objectives.
You're saying that the model that you guys are playing with here is less accurate than the industry, or what do you mean? No, but
Yeah, that's what I'm saying.
No, can you just point at the mouse, please?
Okay, yeah. This is a little bit of a private joke, but each GRN model is very simple to implement. It has a very nice implementation on Loihi, which is why they use it.
Okay.
These Steve and others have used it.
Yeah.
And this is too, so it's supposed to be even better.
Exactly.
But oh no.
Let's move on.
That was too spicy right now.
Well, I think the protocol that has to be.
Sorry, guys, online. We have a fire alarm. We have to move out.
Zoom live. I guess you can take your laptop.
I can see it here.
That's what I'm saying.
First time I get my talk. Right, so I just ended up with the shit-funking HGRN, which actually it is a perfectly valid model to implement on Loihi. These other models are potentially more complicated, so there is reason to use HGRN there. It's just that you can do better. So my talk is basically going to be about, so if we have these learning objectives and these online updates, which look something like learning, so can we actually use synaptic plasticity for self-attention? In fact, synaptic plasticity is something that we can build, whether it's in memoristic crossbar ways or in the Intel Loihi chip we have, or actually in CMOS, like the chips that Giacomo Indeberry is building. So we do have these synaptic plasticity processors or circuits, and we asked the question, like, can we actually use this for building transformers? So I'm sorry, I know many of you know what synaptic plasticity is, so I'm going to go quickly over it. So this is, yes. Yeah, okay, sorry. So this is the classical SDP rule. Basically, when the pre-spikes or when the post-spikes, you basically take the value of the presynaptic trace and add it to the weight value, and vice versa. When pre-spikes, you take the value of the postsynaptic trace and you add it to the weight, or subtract it from the weight value. This is classical SDP, very efficient to implement. Doesn't really work that well in practice. So typically what we do, or what we did in the past also, and did this with Friedemann and Zenke, was that to add another trace to this, which basically tells those two neuron or the synapse, how well it's performing a task. So it could be something like reward or error and so on. And you get these so-called three-factor rules. And the cool thing with these three-factor rules that, well, firstly, they have something like an implementation that looks like SDP, but it also can be, if you derive the synaptic weight update using gradient descent on some local loss function or some loss function L, you also get these three factors. This is just like in the delta rule, right? So you basically have the derivative of loss function with respect to the output, the derivative of the activation function, and the derivative of the inputs. In this case, with the spiking neuron, you would have, for example, its membrane potential. And so you can, these two terms are typically local because it depends on the postsynaptic, presynaptic. This is generally not local if you have one global loss, but you can also have one loss per layer, right? And I'll be talking more about this. So let's, in the implementation of these, I'll quickly go a little bit on the side of why of motivating why synaptic plasticity and actually in later why self-attention is relevant here. So, yeah, so there are some challenges in actually building these synaptic plasticity rules, and some of them are listed here. So one is basically the spatial credit assignment. Essentially, if you want to get the gradient with respect of the loss with respect to the outputs, you have to back propagate through the whole network, which basically is the usual spatial credit assignment problem there's no easy way to solve it in a local fashion. You typically have to have some weight transport in order to solve this. Or use approximations, and these are, for example, feedback alignments, which basically we can broadcast the errors from a global loss function. Or what we think works really nicely is using these local loss functions. So every layer is equipped with its own handcrafted or automatically trained loss function. And then there's no spatial credit assignment because you only backpropagate within that layer. Okay, so these are local loss functions. Just keep the local loss function in mind. I'll come back to that later. This is not completely relevant because I won't be talking much about spiking neurons in the rest of the talk, but we basically solve this spiking nonlinearity with freedom and with these surrogate gradients. Worked very well in practice. It's just a single liner. Who would have known that we can train spiking networks with a single line of code. And the temporal credit assignment, which basically is the story of eligibility propagation. Essentially that you can, instead of back propagating through time, the gradients, you can actually forward propagate them using something that is like RTRL, so real-time recurrent learning. You might have heard this from Anand's talk if you were there when we talked about it. Yeah, so quickly, I'll skip over this just to save some time. Just for my friends at LT and maybe others, generally, in order to solve RTRL, you need to, so if you want to do this with auto differentiation, actually, for example, JAX does have an auto diff mode for RTRL. It's basically the forward mode RTRL. If you do this naively, it's very bad because you do a lot of multiplications by zero. But in fact, in most of the approximations that people use, for example, for EPROP, all of the tensors are diagonal. And so they remain diagonal. And therefore, we developed a library that basically does the auto differentiation in the compressed form, so which is much faster. And so this is where we get speedups, even compared to BPTT that uses this library. So if you're interested, it's called GraphX. And Jamie here spent a lot of time writing that library. He would love it if you used it. Yep.
Is it only for diagonal or?
It's diagonal. Yes, it's for diagonal and block diagonal. And for tensors, I think third order tensors. So there are many different ways of building diagonal tensors there. So he listed all of them, hand-coded all of them. Okay, that was just a side note. Coming back to the spatial credit assignment problem. So just want to remind you of this local loss function. So in a bunch of papers also in the past, we showed that actually, if you have these local loss functions, you can really do a good job in training your neural network, whether you're doing classification or reinforcement learning. And so this is something that I'm going to build on here. Tying this back to the self-attention story. So I told you earlier that we're interested in the methods for doing self-attention updates that are based on gradient descents like this. The question was, of course, what is this loss function? Different people use, of course, different things. You saw that table. Actually, one property of that loss function is that it's local. In fact, it looks something like this, where you have the key multiplies this weight matrix. I think this should be a Q.
You should come to the key.
Yeah. Yeah, I think this should be a Q. Anyway, so it's basically you take an input and you multiply it with the projected with that attention matrix, and you try to reproduce the value. So this is something like a self-supervised loss function, right? You're basically trying to reconstruct your own input. Or you can see this as an autoencoder. And this is, in fact, if you looked at that table, you'll see most of them uses losses, something like this, without my mistake with the K. I'm not entirely sure. I'm blanking on this. And why is this a good thing? In the example that I told you earlier with the book and this free attention, free energy, and information theory. Well, let's say my query, for example, is let's say it's a perfect linear combination of my key 1 and key 2. Let's say this is free energy, this is information theory. Then if I perfectly solve this loss, then my output would be a linear combination of those two pages. Okay, so that's kind of the intuition why you want to use these kinds of self-supervised autoregressive losses. And so this basically relates to the idea that the transformer during inference is actually performing some loss function, so some learning on some loss function. And ideas like this were actually identified quite a long time ago already in the GPT-3 paper. That's already almost 5 years ago, where they show that these language models are few-shot learners. Basically, during inference, they can perform something like few-shot learning. What I'm interested in here is that as we're actually building, when we were creating these even spiking neural networks with local loss functions, there was always the question, what should these loss functions be? We handcrafted them and so on. Actually, this whole transformer story really solved that problem, because what you're doing in a transformer when you train it with these kinds of losses and these kinds of updates is that you're actually learning to learn. You're learning which of these loss functions you should be using locally. When you do inference, you're basically applying that loss function for learning, okay? And essentially solving, if you want, few-shot or even medium-shot tasks. So training a transformer is like constructing a local learning problem by examples. Okay, it's essentially like a meta-learning approach where, and if we plug in synaptic plasticity rules here, we can learn how to learn with synaptic plasticity, which relates to the comment I was talking to Brian about. If you want to plug in like SCDP here, you can basically learn how to learn with SCDP, and it should work relatively well. Okay. And we tried this with different architectures. I'm going to show you some results on this. So this is Jan Finkbeiner. He really wanted to first implement the standard transformer on the Intel Loihi chip using the plasticity processor, since we know that the updates of the attention are actually something like plasticity updates. And you can even do this for the standard transformer. So basically what he does there basically uses something like Hebbian updates to write the KV caches on the memory of the synaptic plasticity processor. And once you get a token, you basically just query that memory and can exactly implement the transformer. Jan really wanted to do this because he could take a pre-trained transformer and just map it on the Loihi chip. And he did this on the OmniGlock dataset. So basically showing that if you're not feeding dogs, but images that look like digits, OmniGlock, basically some examples are here. They're like MNIST, but with many more samples per class. And he got pretty good results, even compared to the gold standard here, which is the model agnostic meta learning, it's a few-shot learning approach. So even on the transformer implemented on the Loihi, he got fairly good results. So these are the two to compare. And of course, as we were discussing several times, the mapping from the pre-trained floating model to the actual Loihi chip is not ideal because of the quantization and so on. These are the models that don't use convolutions. We didn't use convolutions in the Loihi. So this was our first implementation of the transformer using the plasticity processor of the Loihi chip. we also asked the question, so I mean, large scale transformers are nice, but can we also use them for small practical tasks? And we did this, for example, for hand pose estimation using these EMG sensors. So this is basically some sensors that you can stick on the arm. There are, I think, 16 of them. And our basically online transformer did a pretty good job. This again is transformer, not the ones that use these cool weight updates as I showed you earlier. We're still working on that, but the results we get here are very nice, given a very, very small transformer model that had only 90,000 parameters. So this can be implemented really efficiently.
What do you mean with online transformer?
Is that so that you don't need the entire sequence to process it. This is because the comparison was made to other models that actually require the whole sequence we're doing. So online says that you get one token for one input, basically, and then you output that red curve.
Okay.
It's essentially using this in the autoregress, in the generative way. Okay. This I should have said, so this transformer actually uses something called the sliding window attention, basically that as your KV cache grows, you don't want it to grow that much. So instead of, you go back and write the oldest token with the newest one to keep them with the KV cache limited. That's why it's called a sliding window. You basically have an attention slide that is a window over the input tokens. And so Paul Manea and Nathan LaRusso. Paul Manea is a student with Jean-Paul Strecken, some of you may know here. So we thought, so how can we actually implement this in the in-memory processor? And they were motivated by a paper that they were showing that you could do crossbar arrays with DRAM, basically on CMOS. But later we had some people come over and talk to us about gain cells, which is basically a charge-based memory, which you can read out using a transistor. You can read out the current with on the output transistor, which means that basically this is something like a DRAM with non-destructive updates. It is just like DRAM; it does leak, right, because of these of the input transistors that basically dump the charge onto this gain cell. But the whole story about the gain cells now is that you can build very low leak transistors using oxide. I forgot what the material they're called. Anyway, I'm blanking on the name, but so you can actually build these. We don't have that technology yet, but we asked the question, so how can we design an in-memory processor that can actually implement these sliding window attention? By the way, why did we choose gain cells versus, say, memristors? You can see that for every input token, you're going to have to write actually one row of this crossbar array, and you can get thousands of these tokens. And this burns a lot of energy. This is why I was asking questions to Wei yesterday, like what is the energy of actually writing over the reading? And so, but gain cells, the read and the write are actually very fairly cheap. Especially the writes are cheap and they can be done fairly quickly. This is why we focus on these gain cells.
So these are silicon-based gain cells?
These would be silicon. I forget the material. Philip Wong does this, right? So he uses these.
LG0 or
LG. Yes, thank you. Yes, exactly. The LG0 transistors that have very low leak, and so this gives you a longer time constant on these gain cells, which is, by the way, something that we might like to also leverage later.
Yeah, but you can get the same leak in.
Sorry?
SOI, you can get the same very low leak in.
No, it's a lower. So it's a wide bandgap.
It's a wide bandgap.
Yeah, wide bandgap. It's like 10 to the negative 15 or negative 18.
But it's slower than, right?
It's slower though.
Somewhat slower. Yeah. But it's really low leakage.
Okay.
It's not like threshold that, right?
No, it's bank of material.
Just really one wide band. So you have very small leakage.
Yeah, so this part was done by Jean-Paul, a Strachan student, the design. But since they are leaking, so this, if you just map a pre-trained transformer on this, it won't work very well. And this is the part that Nathan, my postdoc, who's now a CNRS researcher, he basically found a way to fine-tune pre-trained transformers to be robust to this leak that you would have in these gain cells. And the results of this is, this is all the design. We don't have the chip yet, of course. So we trained this on 125 and the reviewers are really insisting for 1 billion parameter models. It's a total pain in the ass to train models like this on 1 billion, but we still did it. And so this is basically also tested on the common sense reasoning task. So we get, what we really wanted to show here is that we get results that are comparable to the GPT models, and that if we grow it, actually, the performance increases. A little bit worse than the actual floating point perfect GPT-2 model, but yeah, so as long as we have the improvements, we're happy about that. And so this could lead to promising kind of reduced latency and energy. I should say here that if you do projections of like what would the chip size would be here, I don't have the numbers in my head now, but unless you do 3D, this is a way too big chip, right? Because you need to store all the whole KB caches, 1 billion worth 1 billion bytes worth of KB caches on gain cells. That's a lot of space. You have to go 3D. And use really small
bits when gain cells, not bits, gain cells with all these FETs in them.
Yeah. Well, the design was analog, so basically each gain cell is storing one element of the projected token.
And they're not small cell, they're not 2T0C. So they only need 2 transistors.
Oh, I see. Similar than the circuit before.
Yeah, I think the circuit we had before was a design using the actual silicon, but but doing this with these low leakage transistors is something that we haven't fully explored yet. Okay, so that's for the implementation of the transformer model in memory computing. So there are ways to do it, even to map existing models onto the in-memory processor. But what about these cool updates I was talking to you about for the that are derived from gradient descent? So this is also something that we can do on the Lohi. So this is an ongoing project by Konstantin Kronbichler, who's an intern with us from Imperial College, also with Dan Goodman. So here we're learning essentially the tokens using the simple Hebbian update for now, so no bells and whistles. And this is essentially using the presynaptic and the postsynaptic traces that you ought to get for free on the Loihi chip. And this is pretty cool, by the way, right? The presynaptic trace is a convolution of your input spikes. And for example, in some of these transformer or Mamba architectures, you already have convolutions on the tokens in your architecture. This basically you're getting this almost for free in your architecture. And you can do these weight updates that perfectly reflect what should happen in your linear attention model. And this is basically the results that Konstantin gets. It's built on it is on the linear regression task. For those who know it, I don't have time to explain it here, but the bottom line is that if we do this on floating versus the quantized model that would run on Lohi, we get similar results. So this is also a type of in-context few-shot learning task. Okay. So here's the part that we're working on right now, which is about in-context learning and continual learning. So why continual learning? Well, if you actually now let's come back to this story of writing a book. Now, if I'm actually updating the weights like this, right? It's like a Hebbian updates, I am going to start to overwrite the previous memories in my book. It's as if I'm going to forget the first pages of my book, and I only remember, say, the last couple, right? Why does it do this? Because these updates are interfering with the updates that are already stored in that memory. It's a classical catastrophic forgetting problem, and it's completely expected because we're basically seeing these input tokens one after another. So eventually, we're going to forget. And in fact, if you look at the models, the capacity of these types of models, even those like Mamba and so on, see actually that their ability to recall, which is from 0 to 1 here, versus the 0 to 1 here, versus the recurrent. So the size of this W here, see that if you reduce the size of that attention matrix, the accuracy goes down. A transformer will solve this perfectly, right? With this recall task. I'll give a little bit more details on what that recall task is, but basically you want to recall some value that's early in the sequence at the end of the sequence. So there is a problem, a practical problem here, in remembering and processing the old input tokens. And so what we thought here is that, I was part of the L2 Life Learning Machines program in DARPA, so continual learning was really in my head for many years. And we thought, so let's actually use the methods that can solve this catastrophic forgetting problem in this attention mechanism. And one way to do this is called metaplasticity. It's by far the coolest method to do it, not the most effective way of doing it. But essentially what you do here is, let's say you have some task A and some task B, right? So the best parameters for task A, let's say, are in the middle of this blob here, and the best parameters for task B are somewhere here. Yes.
Sorry, I'm a little bit delaying the thought. In the previous slide, you talked about transformers versus state space models. For catastrophic.
Right.
Right. Okay, because you didn't.
Because you don't have a catastrophic forgetting transformers because you remember everything.
Everything, exactly.
In this case, you're actually loading these KB caches on a fixed memory. You are eventually going to lose the memory. So that's just like the argument.
At one point here, because you hinted at before, this is essentially what a Hopfield network does, right? A linear Hopfield network.
Yeah.
What I find a bit funny is that to make Hopfield networks better, people added this softmax function to increase the capacity with the modern Hopfield networks. But the transformers here, the linear transformers and state space models went the other way. They started with a function that has the softmax, and then they removed it. Have a simpler model, which is now equivalent to the traditional Hopfield network. Right. And now they have a memory.
No, but look, the Hopfield network is different here, because in the Hopfield network, you see the whole input batch at the same time, right? So I understand this relates to this capacity idea, but the way that you actually load the memories is different here. You really learn them one after another in this case. Right.
I think that's, still for the storage of the network, I'm pretty sure if you, instead of doing this update, you did the update that the modern Hopfield networks do, where instead of just adding on top of the weight matrix, you also have a softmax mechanism, or for reading out at least with the softmax mechanism. Yeah. Maybe you wouldn't have this capacity problem. So I'm just wondering if this is the price that you pay for making the networks easier.
Yeah, I heard also, I think it was, you were mentioning the softmax on the Hopfield networks. I'm not sure exactly what you're referring to, but I'm happy to discuss it later. I mean, the softmax, if you put it at the output, it's just going to clean up your data, but it's not going to increase your capacity. That's 0.14n. I don't get that.
I think people have argued.
No, it does increase capacity a lot.
Oh, it was you. You mentioned that, yeah.
Yeah. But what it's proposing is using a sliding window where you have a Hopfield network and you just keep updating the whole thing with the sliding window. Is that what you're saying, Johannes?
Kind of.
Let's discuss this later, because I'm not. Yeah, I'd like to understand that better. Exactly what you're referring to. Okay, so we have these two tasks.
Weight consolidation, right?
Yeah, this is elastic weight consolidation, exactly. So basically, what you do is that instead of, it's like, if you want to learn task 1, so you get here, and you want to learn task B. If you do nothing, if you just do it naively, you would end here, which is good for task B, but it's bad for task A. So instead, you can actually change the update rule such that you end in a region that overlaps. So it's a good solution for both tasks. Okay, that's here. And this is what elastic weight consolidation and plenty of other methods are doing. Basically, you have your original loss function here, and you add another loss that basically anchors you to the previous parameters. And this generally works quite well. Elastic weight. Yeah. Well, okay, it doesn't work that well, but we have something better. It does kind of work. So
kind of works, yeah.
And so this is where we had so Joan Bonnet, who joined us from Damien Carlio's lab. So he is this guy's Bayesian from inside out. So he really wanted to apply Bayesian learning to this continual learning problem. And essentially, one of the main problems, by the way, with elastic weight consolidation is that they have a finite capacity, right? So, and as you're learning, you will eventually, you'll just stop learning, right? And so this is what happens here. For example, if you, let's say this is the case if you have no methods. Basically, you come in with different data samples, and at the end, you can learn what the panda is. That's great, but you've forgotten everything else. But if you use these elastic weight consolidation and other methods, essentially you can learn the first task pretty well, but eventually you're going to hit a wall because you've exhausted the capacity of your network, and you're not going to be able to learn further. This is one of the big problems of elastic weight consolidation. With this Bayesian learning that John developed, actually what you do is that you just say that you basically pose the problem as a Bayesian learning problem, and just assume here that you basically truncate that Bayesian learning problem to the last n samples so that you can actually remember the last n samples of this that are presented to you and forget the old ones. Okay. And the nice thing here is that as you pose this as a Bayesian learning problem with the variational methods, essentially you can come up with a learning rule on the weight updates that tells you how you should update your weights. So mu is basically going to be the mean of your variational distribution that describes your weights. And the sigma is going to determine is the uncertainty of those weights. Why is that uncertainty useful? Because that uncertainty actually tells you how sure you are of a given weight, provided what you've learned in the past. So if you think that a weight was important, it's going to have low uncertainty and it's going to be harder to change. This is exactly what you want with metaplasticity.
So how do you choose n?
How do you choose n? So in this case, John chose it by hand. So he says, this is how much I want to remember, but I'm not there yet, right? Just hang on for one slide. This is going to be really cool. And so this is a method that really outperforms other methods out there, including elastic weight consolidation. And it has a mathematical basis for it, which is Bayesian, which John's very proud of. And it really is going to be useful for us in this way here. So now coming back into this to this story about the local loss function and self-attention. So we have exactly the same problem. We have a local loss function that we want to learn. We're getting tokens one after another. We don't want to forget them, but some of them maybe we do want to forget, right? Because they may be irrelevant. And so we can essentially apply the methods that John developed, which by the way, I didn't say the name, is metaplasticity from synaptic uncertainty, so MESU. And so we can apply it to basically the loss function here written in the negative log likelihood form. The cool thing with this is that we have an analytical solution of this loss function in this probabilistic sense, and so we can derive weight updates, basically the updates to our parameters mu and sigma, just as John did for his continual learning problem, but now for self-attention. So this is why we call it metaplastic self-attention or Bayesian metaplastic self-attention or BMA. So what we have here are basically now two states, right? And usually in SSMs and self-attention or linear attention, you have one state. And what metaplasticity tells us is that you need to have two states, one that remembers actual weights, the second that remembers how important those weights were. And you get an update that's basically derived from this local loss function here. Coming to the end here, now, this whole story, this whole update is something that you're going to train, right? Now you plug this in a transistor, in a transformer, you're going to train this. So you can train n. You can learn to learn the n. And this is exactly what we did.
Well, where's the end there?
Here. Okay, sorry, I got ahead of myself. So the n here basically tells you is your memory window, right? So beyond that, you're just assuming that you don't remember the sequence of inputs, you're going to start forgetting. So it's how much you want to remember.
Have a hard window because it's like an filter. It's like an IO.
It's not a hard. You're right. It's not a hard window, but at some point,
parameter, like
you will. Yeah, you will. Those memories will decay. Yes, that's right. And so the way that we use this is basically in the mode where we don't use the uncertainty explicitly. The weight updates are basically Argmax, so the maximum a posteriori of that variational update, and then the output of our self-attention is going to be the usual Q times that W. Yeah.
And this is not online here.
This is what?
Not an online learning.
No, it is online. This is purely online. Why do you think? Why do you say it's not online?
But n, how do you find n? Then you have to have.
Oh, okay.
Yeah.
So there's two things here.
Okay.
There's two things. So this is a learning rule, right? If you can think n as a hyperparameter, but
Okay.
remember, this is going to be inside a transformer. You're training the model, so you're training the hyperparameters.
Okay. Yeah.
Pre-train, then doing you can see.
Yes, exactly. You pre-train. You pre-train.
train and then fix the n, and then you go and you put
Yeah.
in. I'm sure we have.
No, the N is inferred by the network. No.
No.
It's not inferred. So this is learned. Of course, you can also have projections to the end, so it can depend on the data dependent way. Honestly, I don't know if John did this or not, but yeah, it's fixed.
So in terms of computation, how much more computation do you add?
Well, you basically add another equation here. Yeah, it's actually our updates are pretty much the same speed as Mamba. It's a little bit slower, but it's all.
And because you just count, I mean, there's nothing.
There are some additional I'm not going into the details of what's happening here. We did have to do one approximation, which is that, as you're doing this in with variational inference, the variational function is here, the Gaussian. And so we're only assuming that we're only taking the diagonal of the cross correlations. And so there are some approximations that we do here.
Yeah, no.
It's like people did with elastic weight consolidation, but this was necessary to accelerate this using the trending kernels. So we tried this on the this associative recall task. I mentioned this earlier, but basically this task is that you come with a sequence of keys and values, right? And in the second half, you want to recall the value associated with a key, something like this. So this is the input sequence, and you look at what is the percentage that you recall. And oops, sorry, it's a little bit overflowing here. And so we compare this to the other methods here. So Mamba is pretty bad at this task generally.
Can you tell us the axis?
I can tell you the axis. So the bottom axis is the model dimension. So it's how large your W is going to be. And the y-axis here is the accuracy of that recall. And so BMA and BMA-U are our methods. And so they're compared to Longhorn, which was at the time when we were working on this was the state of the art. I think it might still be, which is also very similar in its architecture and weight updates, but it doesn't have this continual learning idea. It doesn't have those two states. And so, yeah, so we're doing pretty well here on both problems. The reason, so for this BMA-U, this is a little bit of our latest creation here, which is that the output of our self-attention now we also have a variance, right? We can tell how sure we are of a given output. And so this BMA-U is using that explicitly, but and basically halving the size of the weight matrix, which is why it's slightly lower. Okay, the green is actually a fair comparison to the red and the blue for reasons I'm not going to go into that have to do with the number of parameters in the model. So we're still basically up there in the state of the art. For the moment, we're still training on very large models, but we did this on the open web text, which is basically the baby model of language modeling. So we're also performing pretty well, especially on basically on these shorter sequences. We were hoping that would be better on longer sequences. I should mention here that we think that actually BMA is going to work very well on problems where you want to explicitly forget some previous tokens and end on small models. So that's what we're looking for here. So this is just a proof of concept that things are working. We tried training this on FineWeb Edu. We're not getting great results for now. And we think this has to do with the fact that most of the other models that are trained in the literature actually use the transformer architecture. But we decided to use, unfortunately, the Mamba architecture, which has a lot of stability problems. Sorry for the technical details. And since I'm working on the LT Shout group here, helping out there, so I thought let's just replace the HGRN block with BMA. And of course, I'm going to show this, otherwise it performs much better. Guys. Okay.
Is it show?
Okay, but so these so this is the automatic speech recognition task. So basically you get the data samples from LibreSpeech, you transform them into these MFCCs and feed this into your sequence model and try to predict the letters, the characters.
Right.
And so this is showing the training loss and the token accuracy. Token accuracy is actually, so it's 18% here, which sounds really low, but it's actually, as Sander was talking about it on Friday, it actually performs, even at 80%, it does a pretty good job.
What's the word error rate? Just so we have some scale.
The thing was in the 20%. I can't remember. Yeah, but it was, I mean, it was comparable to HGRN, and somehow much better than the transformer model, which I don't GPT-2. I'm not sure why. Yeah. So anyway, just to show that this also works in the small networks, is basically are less than 1 million parameters. I should mention here that the BMA always has twice the state size, right? Because you also have the variance here. Okay, so this is my last slide. So this whole story with the self-attention to and synaptic plasticity for me is a great way of seeing how we can actually learn to learn. So we have these beautiful synaptic plasticity rules that we can develop on hardware, but there, as you know, Toby would say, there's no problem that really requires online learning. And I think that's wrong. If you see it actually in this transformer approach, you can actually have these learning rules built in that transformer model. And once you're done training this on a big computer that uses a lot of energy, well, you just map it onto your neuromorphic device, and that you can actually do learning, essentially inference, but still learning on your neuromorphic device. So for me, this is a way of actually doing hyperparameter exploration, architecture exploration, however you want to call it, evolution, structural learning for neuromorphic hardware. Yeah, and so just want to thank all the people I worked with. So this is both my group and John Paul's group, and the people who worked with us and the people who funded us. So thank you.
And we have the next talk is an online speaker. So yeah, we can't tell him to like delay further. So we'll be back with him.
He's gonna go sleep.
No.